So here we begin Chapter 8. Chapter 8 focuses primarily on chemical bonding. Now there's multiple types of bonds that can form, and we've already talked about some of those. But before we do that, we really should ask the question, why do bonds form? Because we actually very rarely find single atoms of elements. Even when we have a pure element, in most cases, that pure element is multiple atoms of that element. So for example, if we have pure hydrogen, we generally don't have individual hydrogen atoms. What we have is two hydrogen atoms bonded together, H2. And the same thing is true for most elements. So clearly there's something happening that makes bonds want to form. And that key issue is that atoms want to be more stable. And so they're going to do whatever they need to do to achieve their most stable state. And in most cases, that's an electron configuration that matches a noble gas. Now, we've seen this already for ionic bonds. We might not have thought about it in this way, but let's think about what happened with ionic bonds. Let's bring up our periodic table. So here's our periodic table. And let's think about some of what we saw. When we were dealing with ionic bonds, recall that metals, which generally we've now learned have low ionization energy, would lose electrons to nonmetals, which have high electron affinity. But what were those numbers of electrons? Well, let's think about magnesium, for example. What charge does magnesium like to take on? The answer, like most elements in that column, in that group, it takes on a +2 charge. Well, if magnesium takes on a +2 charge, it now has the same configuration as neon. How about group 3 or group 13? Gallium. We said gallium likes to take on a +3 charge. Well, when it does that, it will adopt the configuration of argon. And so that's going to be true for pretty much all of these charges that we talked about. Same thing is true for the anions. Bromine, for example, takes a charge of -1, which gives it the same configuration as krypton. And so that's what these elements are trying to do. They're trying to gain or lose electrons so that their configuration matches that of a noble gas. Now, in the case of ionic bonds, which are what we were discussing previously, we would form a cation by the metal giving up electrons, the nonmetal gains electrons, forms an anion, and the opposites attract to each other. What about two nonmetals? Well, that's when we get covalent bonds. In the case of two nonmetals, we don't actually transfer the electrons. These bonds are formed by sharing electrons. And they can be in one of three ways. We can have a single bond, a double bond, and a triple bond. And the difference between these is the number of electrons that are shared. So a single bond shares 2 electrons. A double bond shares 4 electrons. And a triple bond shares 6 electrons. So why does this take place? Again, it's so that we can achieve a noble gas configuration, and this desire to achieve a noble gas configuration by acquiring, or as we saw with some of the metals, losing electrons, is known as the Octet Rule. So in other words, every element wants to gain or lose electrons in order to match the configuration of a noble gas. Now, not every compound, every molecule, every element follows the Octet Rule 100% of the time. And we do have a few exceptions. What are the exceptions? Well, anytime we have an odd number of valence electrons, and I shouldn't just say valence electrons, but total valence electrons. So in other words, if we add up all of the valence electrons in all of the molecules that are bonded, if that number is odd, such as in the molecule nitrogen monoxide, here nitrogen has 5 valence electrons, oxygen has 6, and if we add those together, we get 11 valence electrons total. And so in a case like this, one of the elements will not have an octet or 8 electrons. The second exception are group 13. So boron, aluminum, etc. These will often have only 6 electrons. And then finally, third row and below, can exceed 8 electrons. Usually 10 or 12 due to d orbitals. All right, now how do we show this? And what do we see? So from this point on, it's very, very important for us to start looking at what we call Lewis structures. Lewis structures are a method for actually showing all of the bonds within a compound. So in other words, if we have methane, CH4, as opposed to just writing out the chemical formula, we will actually show all of the bonds and all of the valence electrons where necessary. So what this shows us is that we have a carbon in the middle, and then each of these lines here represent single bonds, which are 2 electrons, and show that each hydrogen is attached to the carbon by a single bond. So the question we should always ask at this point, once we've drawn a structure, is, are all of the atoms happy? Or in other words, do all of our atoms here have an octet? So we look at carbon. This carbon here has 4 single bonds. Each single bond is 2 electrons. If there's 4 of them, that means we have a total of 8 electrons around that carbon. So the carbon is happy. What about the hydrogens? Well, each hydrogen has 1 single bond, which means each hydrogen has 2 electrons. Now 2 is obviously not 8, but turns out that's okay. Why is that? Well, hydrogen being in the first row, the nearest noble gas to hydrogen is of course helium. Helium only has 2 electrons. So in the case of hydrogen, it's not going to go to 8 total electrons, it's only going to match helium, which is 2 total electrons. All right, now why do we need to do this? Why not just stick with what we've done, which is to draw, chemical formulas? Well, the problem is chemical formulas don't always give us the full story. So let's say I asked you about C4H10. So you could draw this compound. Or you could draw this molecule. And what's important to follow here is the pattern of the carbons. In the first molecule, the 4 carbons are in a straight line. But in the second molecule, there's 3 carbons in a straight line and 1 branching off. So that tells us these are not the same molecule. And so what this really means is that if we want to know what compound we're talking about, the chemical formula by itself is not enough information. So if we want to know what compound we have, we either need to draw a structure showing all the bonds, or we need to name the compound. And in this case, you might say, well, there's only 2 different compounds here. That's not a big deal. But what if we have more carbons? So you can actually determine this. And so look at what we can see on this chart. So if we have, for example, 8 carbons, there's 18 possible molecules. Up to 10, and we get 75 possible molecules. Go up to 20, and there's 366,000 possibilities. And these numbers are just going to keep getting bigger. What if we had 100 carbons? So what if we had C100 H2O2? How many different molecules do you think you can draw, or that there could exist with that chemical formula? Take a minute and make some guesses. So I would guess at this point it's probably a safe bet that no matter how many you guessed, you probably came up with a number that was too low. Because you can see down at the bottom just how many compounds are possible with 100 carbons. Now, how do we draw these Lewis structures? Well, there's a fairly straightforward set of rules that we can follow in order to do this. So step 1, sum up all of the valence electrons. Step 2, connect atoms to the central atom using single bonds. Now, how do we determine which atom is the single atom? Well, often your central atom is going to be the atom that needs more electrons. So an atom like fluorine, for example, has 7 valence electrons. It only needs 1 more. So it's only going to form 1 bond. But an element like carbon, which has 4 valence electrons, needs 4 more electrons. And when we form one of these covalent bonds, the covalent bonds are, in general, formed by each atom using 1 of its electrons. So carbon is going to need 4 bonds to have an octet. And so carbon would be much more likely to be a central atom than, say, fluorine. So again, those first 2 steps, we're going to sum up all of our valence electrons, and then we're going to connect atoms to the central atom using single bonds. Step 3. We're going to complete octets on the outer atoms using lone pairs. So lone pairs are pairs of electrons that are not part of a bond. They're just specific to one atom. Once we've done that, we place any leftover electrons on the central atom. At this point, we should check all of our atoms for octets. If everyone has an octet, then we're done. But if our central atom does not have an octet, then we can use double and or triple bonds as needed. All right, so let's try this. NF3, nitrogen trifluoride. So step one, sum up all of your valence electrons. So when you're working on these, you'll probably want to have a periodic table in front of you. But nitrogen has 5, fluorine has 7. There's 3 of them, so we multiply that by 3. So we get a total of 26 valence electrons. All right, what goes in the middle? Well, if we think about what each of these need, nitrogen has 5 electrons. It's going to need 3 more. So it's going to need 3 bonds. Fluorine, on the other hand, already has 7 electrons, only needs 1 more. So we'll put nitrogen in the middle, and it can bond to each of the fluorines. Now, I often find it helpful, especially if this is something that's completely new to you, to keep a running total of the electrons that you've used and what you have left. So we had 26 to start. For these 3 single bonds, each single bond has 2 electrons, so we've used 6 of our electrons. So we now have 20 electrons left. All right, next step is to complete the octets on the outer atoms. So each of these fluorines already has 2 electrons from the single bond, so they need how many more? They each need 6. So we can do that by putting 3 lone pairs on each fluorine. So now all of our fluorines are happy, and we've made 9 lone pairs, so that's another 18 electrons. So we have 2 electrons left. Where do those last 2 electrons go? Well, now they go in the central atom. -2, and we have no electrons left. Final question. Does everyone have an octet? Is everyone happy? Each of the fluorines have 3 lone pairs and 1 bond, so fluorine is happy. The nitrogen has 3 bonds and 1 lone pair, so that's also 8 electrons. The nitrogen is happy. Have we used all of our electrons? The answer is yes. And so since all of the atoms are happy, we've used all the electrons. That's our Lewis structure. And so no, don't forget this last item. You have to use all the electrons. If you haven't used all the electrons, then that's not a correct Lewis structure. All right, let's do another one. Hcn. Cn minus is a polyatomic that we didn't cover in our previous classes, but is known as cyanide. You might be familiar with this ion if you like to read mysteries, especially old mysteries. Alright, so we need to sum up all of our valence electrons. That's 1 for hydrogen, 4 for carbon, and 5 for nitrogen. So 10 electrons total. Now, what goes in the middle? Well, what goes in the middle is carbon, because that needs more bonds than either hydrogen or nitrogen. Now, let's connect that using single bonds. We have 6 electrons left. So where do those go? Well, we said the next place to put them is on the outer atoms. Hydrogen doesn't need any. Hydrogen's got its 1 bond, which is what hydrogen will always have. But nitrogen here needs 6 more electrons. So minus 6 equals 0, and we've used all of our electrons. Is everyone happy? Hydrogen's happy, nitrogen's happy, but carbon only has 4 electrons. And so that's something we're going to need to fix. The problem is we can't just add lone pairs to carbon because we don't have any more lone pairs to add. So what do we do instead? Well, now we're going to take away one of the lone pairs on nitrogen. And we're going to make a double bond between carbon and nitrogen. So nitrogen is still happy. It still has 8 electrons. It has 2 bonds and 2 lone pairs. Carbon's not happy yet though. It's better. It has 6 electrons from the 3 bonds, but still not where it wants to be. So what do? We do it again. And at that point, carbon has 8 electrons, so does nitrogen. Hydrogen has its 2 for an octet, and everybody's happy. All right, let's do one more example before I give you some practice to do. Let's do NH4+, or ammonium. So how many electrons here? Well, we know nitrogen has 5. Each hydrogen has 1. There's 4 of them. But what happens to this plus charge? Well, as with a single element, we have a plus charge. That means we've lost an electron. So we need to subtract 1 here. So we have 8 valence electrons. So nitrogen in the middle, single bonded to each of the hydrogens. And we've used all of our valence electrons. Is everybody happy? Yes, everyone has an octet. But what about that positive charge? Does that need to show up? And the answer is we add it in by doing what we call formal charge. So a formal charge, we say, is essentially a bookkeeping of electrons. And all of the formal charges within a molecule need to add up to the total charge of the molecule. We add up, or we calculate formal charge as being equal to the number of valence electrons, subtract out the unshared electrons, and then also subtract out any shared or bonding electrons divided by 2. So for hydrogen here, hydrogen usually has one valence electron. It has no unshared electrons. Unshared electrons are the lone pairs. But it has 2 shared electrons from the bond. So 2 divided by 2 is equal to 0. So there's no formal charge on the hydrogen here. What about the nitrogen? Well, nitrogen has 5 valence electrons. It has no unshared electrons here, but it has 4 bonds, or 8 shared electrons, which we divide by 2, gives us +1. So when we draw this structure, we should put our formal positive charge in on nitrogen. Alright, so that's how we draw Lewis structures. So at this point, you should get out in-class exercise number 10, labeled Covalent Bonds and Lewis structures, and start working your way through those examples.